I'm going to shed some light on the project that has been mentioned a couple of times already. It's called CRIU, or how we call it, CRIU. So CRIU, it's an acronym. It stands for Checkpoint Restoring User Space. It's a project that we started several years ago as an attempt to implement checkpointing and restoring functionality for the Linux kernel. There has already been several attempts to implement this by that time, but they all have failed for several reasons. So CRIU was yet another attempt that tried to take Linux kernel community opinion into account. We started CRIU as a low-level system tool, but a user space tool, which does these two things. It takes a Linux process with everything it's using, memory, files, sockets, all the environment, including sessions, C groups, and namespaces, or living in containers. And CRIU was about to take a snapshot of this state and write this state into a set of files on disk. And the state was an information that should be enough to restore the same set of processes later or maybe on another node, provided the kernel support would be there. Initially, when we started CRIU, we wanted to use this checkpoint and restore functionality basically for two things. First was live migration of containers, when we took a container and moved it seamlessly to another node. The second thing we wanted CRIU for was seamless kernel update. It works pretty much the same, like you checkpoint your container, then update the kernel and restore it back. So it looks like live migration, but without actually changing the hardware node. So all the containers stay on the same server. But soon after that, we've get feedback from people looking at a project with us. These guys started to use CRIU for various other things. For example, they did it for advanced debugging, for advanced testing. HPC people started looking at CRIU to make periodic snapshots of their computational jobs so that if they have power outage in their data center, they do not start recomputing all this stuff from the very beginning. It usually takes long, like weeks. By today, we have made many releases with CRIU already. We can dump and restore pretty much random process. However, it doesn't work in like 100% of the cases. It's mostly because of we're playing catch up with the kernel. Every time some new API or new feature appears in the kernel and applications start to use it, CRIU may not yet know how to work with that. Last time, it was about in-kernel asynchronous I/O. Before this feature appeared in the kernel, application did asynchronous I/O in the user space. They spawned threads, which did reads and writes. Then there appeared a system call on the kernel side, which created asynchronous I/O context. But applications didn't use it because they had the user space asynchronous I/O. And we didn't implement it in CRIU. But first time we've met MySQL database, which started actually using this stuff. We had to implement the necessary support on the CRIU side too. And this thing will continue forever, of course. Every time any new functionality would appear in the CRIU, in the kernel, we'll have to do necessary support on the CRIU side. And we are constantly talking to kernel guys to keep us up to date and not to implement APIs in a manner that cannot be checkpointed or restored. Other than just support for saving the state and restoring the state, in CRIU we have support for live migration. As Tycho told already, live migration is not when you just save, copy, and restore, because this middle part, when you copy stuff between servers, may take long, depending on the size of the image files. For truly live migration, you have to copy as much stuff in advance as you can. So in CRIU, we have support for iterations when you read the memory from processes, copy it to another node, but processes continue running. After that, CRIU should be able to get what has changed since last time. This is done with the kernel help, of course, and it's already there in CRIU. Also, we have in CRIU as well support for transferring images over the wire immediately without the need to put them on disk on both nodes. This also improves the freeze time. We have integration of CRIU with most important container solutions so far. We have integration with LXC, with OpenVZ. Integration with Docker is currently work in progress. The guys has put full support into run C part, but as far as Docker itself, with Docker daemon and Docker command line tool is concerned, it's not yet there. The pull request is open on the GitHub. It is. Yeah. And also, since image files that CRIU generates are actually binary, you cannot read them with text editor. We have a tool called CRIT, which allows you to read the image in human readable format. Effectively, we convert the images into a JSON file. And another quite cool feature of CRIT is that you can modify this JSON file and pack it back into binary format CRIU understands and try to restore from what you have created. This allows to, for example, modify stuff on the fly. You can live migrate a container, fixing various bits while it's being migrated from one node to another. It's possible, though, there is no API knobs to make this happen yet. So this is what we have so far. What's coming next? The next is we want to make CRIU 2.0 release this spring. Like 3 or 4 releases ago, we decided to do time-driven releases, and we do it 4 times a year in December, March, June, and September. The next release is planned for the beginning of March, and it should be 2.0 already, in which we slightly toss the code around the source directory, but that's not the most important thing. The most important stuff about 2.0 is that we will try to make 2 interesting technology that were implemented in CRIU. We want them to be available independently. The first thing is what we call compel. Compel is a framework that allows you to inject parasite codes into running processes. Briefly, it works like that. You write a C program, a tiny C program, then you compile it with a special set of flags. The compile tool will tell you what flags are needed for compilation. Then the objective file you get should be linked with compile libraries. It will also help you with doing this. And the resulting ELF file you get, you will not be able to launch it from the command line. It's not an executable you normally would pass into the exec system call. But instead, this ELF file you would get, you will be able to take it, take a random running process, and put this binary into the process and make this process jump into the entry point of your blob. So effectively, what you will have, you will make a random process execute the code you want. Of course, all the kernel security restrictions will be respected, right? It will be done with a debugging interface. So if you are allowed to debug your process, then you will be able to make it run your code. If you are not, then you are not. We use this thing in CRIU to get state of running processes, but in the current implementation, this functionality is very heavily tied to the rest of the CRIU code. There is no way to use it independently. And we've been asked for several times whether it was possible to use it independently. This March, with CRIU 2.0, this functionality will be available as an independent piece of code, and hopefully as a separate package in distributions that will be interested in this. The second cool stuff that we have in CRIU, and it was asked about on the Taiko's talk, is how CRIU live migrates TCP connections. When we started CRIU several years ago, as I told, the plan was to live migrate containers, and the main way you communicate to containers is via the networking, via the TCP connected sockets. So live migrating a socket was an important feature of CRIU from the very beginning. So what we did was we patched Linux kernel, and the patches hit 3.11, so they are available in pretty average distribution already, which allow us to suspend the TCP socket, get information about the connection state out of it, put it into a CRIU format or in any other format, and then to recreate the same socket from scratch, even on another node. And the connection goes on. The peer of the socket doesn't notice that something has happened. From the remote side, it looks like if there was a small glitch in the networking. Several packets were dropped in between, depending on the gap between suspend and resume. This is, as I told, in kernel 3.11 and above. This is in CRIU, but just like parasite code injection, it's heavily tied to CRIU. There is no way to use it independently. Well, you can copy and paste the code from the known places, right? But it's not a convenient way of doing things. So the second thing that appears in CRIU.0, we hope, is a library called libsoc checkpoint restore, libsoc-cr, which will provide an API for suspending TCP connections and resuming them back. This is the stuff we already have implemented, and we plan to slightly reformat the code to make it available. But other than this, there are several stuff that has popped up on the CRIU project that hasn't yet been implemented, but these three are very tempting. The first thing is binary logging. In CRIU tool, there are 4 levels of verbosity, like 0, 1, 2, and 3. Depending on the log level you choose, CRIU prints less or more messages inside log file. But eventually, it has turned out that only 2 of them make sense. The first log level that makes sense is the maximal verbosity when CRIU prints everything it does. Decreasing it to the second one doesn't make sense because CRIU prints some information, but when something bad happens, there is not enough of logging to find out what has happened. We always need full log to debug a problem. As opposite to the maximum verbosity level, another log level that makes sense is complete silence. Since on the maximal logging, CRIU prints tons of messages, it typically slows down the dump processes 10 to 20% of time, depending on the size of an application. But what we have seen so far was 10 to 20%. It can be critical for live migration, where we fight for every fraction of a second. So for the fastest live migration, you should just turn off the verbosity, shut CRIU up not to print anything. But in this case, if something goes wrong, we will have no idea what to do with that. The checkpoint failed, but we cannot debug it. What we want in CRIU is to provide some ability for the tool to print logs, not inside log files, but in some region in the memory in a binary form that doesn't slow things down significantly. This is possible from what we have seen because we use glibc fprintf function to print logs, and what we found out is that up to 50% of time spent inside this function, glibc scans for the arguments inside the string and pulls them from the stack. If we will be able to get the arguments without the scanning, we will already save a big amount of time. The other big portion of time is spent in writing data into a file on a disk. Despite the file is in cached mode, the time spent inside the kernel to find the cached page and copy data from user space to the kernel also matters. So if we have an ability to print logs quicker in a memory region and only on error printed inside a file, that would be useful. But as I told, this thing is not yet there. It's an interesting challenge we've faced. The second thing, which unlike binary logging is already work in progress, is advanced process interface in the kernel. To get information about processes, CRIU scans for tons of proc files on the host. I would say it opens like pretty much every file under proc PID directory to get everything. Information about memory, about open files, sessions, PIDs, hierarchy of processes, and so on. And proc works slowly. Like you have to open many files, you have to scan them. Kernel would convert internal kernel objects into strings with printf-like function. Then it will copy the information to the CRIU buffer. Then CRIU will convert the information back into a binary form, like scanning a number from string into integer, right? Then closing the file. Surprisingly, but closing files in proc takes 30% of time of CRIU dump. So what we've asked kernel community for, and actually provided them the initial set of patches, is a netlink socket that can dump you into the user space and information about tasks. And this information is dumped in an extendable manner. If you ever worked with, for example, SS utility, does anybody know what SS utility does on a Linux? SS prints you information about sockets in the system, about TCP connections, about UDP connections, about Unix connections. Each connection may have lots of attributes that make sense to this tool. So SS has lots of command line options that can, with which you can specify what information you want to get. And SS uses netlink interface, asking the kernel for only the required information. We want the same for processes. Like we will tell to kernel, tell us the PIDs. It will just return us a stream of integers instead of calling read dir on proc. Then we will tell to kernel, OK, tell us everything about this PID. Kernel would report a big blob with field structure instead of opening and reading tons of files. And the third thing that has appeared in CRIU is not a technical one, but rather an academic. How many of students or postgraduate students doing research here, or only developers? Are there students in the room? No? That's a pity. OK. So it's an interesting challenge. Like, consider you have a graph of objects. And you have rules of adding new items to this graph. And the rules are quite complex. For example, you cannot add a random node to a graph, but instead you can only clone an existing one. And if you clone it, the edges that come from the original point to other ones are cloned too, but with some changes in it, right? And you have a task. You have an empty graph with a single point, and using the rules that I described, you want to get some graph that is described in an image file. This is what CRIU restore does. It wants to create processes and create files and memory and sessions and everything without using an API that can just create processes, files, sessions, and so on. It can create processes, but it cannot create sessions. Session can only be inherited. And there are lots of such limitations. And right now in CRIU, all this stuff is solved using lots of ad hoc algorithms. Like we know that processes can be forked. Okay, if we have a tree, we try to fork it. But sometimes process can form a tree that CRIU algorithms fail to dump and restore. If we have a mathematically proven solutions of how to create such graphs, that would be awesome. But by that time, we don't have such a thing. So the main part is over. If you want to find out more about CRIU, CRIU is an open project from day zero. It sits on the CRIU.org website. It contains all the docs, plans, and news. We have Google+ page and Twitter account where we publish news and thoughts on the project. If you want to take part in development, there is a mailing list at openvz.org. And the source code sits on the GitHub on my account. There are issues that were planning to fix soon on the GitHub, but unfortunately, we do not accept pull requests, and there is no way to turn them on GitHub because everything happens in the kernel style on the mailing list, but still. So this is all I have. If you have any questions, you can ask them now. Yeah.
When you use CRIU to dump a process so that you can debug it later, if it's got an OpenTCP socket, is it possible to create a knock that can talk to that once it's restored?
So the question was, if I save a process that had a TCP connection and I want to debug it later, is it possible to make the restored process talk to someone else rather than the original client, right? It's possible, but we do not have any automation for this. You will have to recreate the peer manually, and then CRIU would restore it for you. Provided you have net namespaces and roots configured properly, it will continue working. It's completely in the mainline kernel. I'm not sure about vanilla Debian, right? You have to check the kernel for at least version. All we need sits in 3.11. But some functionality is hidden under kernel configuration options, so some distributions might have chosen to turn them off. I cannot say for sure. What I do know is that Fedora 19 and above, they have all this stuff turned on, and there is even CRIU package on their repo. Debian 8 has 3.11, if I'm not mistaken, but I haven't checked whether everything is turned on. In any way, there is an action of CRIU tool called check. You can run CRIU check, and it will tell you whether kernel support is up to date or not. Now, what's the status of the netlink dump? You mean this infrastructure for reading information from the kernel about process? It's in patch send. We've sent the patches. Someone from the kernel side has reviewed it, had some comments. We have resent it, I don't know, maybe a couple of weeks ago, and so it's still on the mailing list. The question was what architectures are supported. We've started with x86 64 bits. This one is fully supported. Then we had people from Qualcomm adding ARM support and ARM 64 support. But this one sometimes doesn't compile on ARM because there is only one guy watching on this. Then we had IBM people porting it on PowerPC 64 bits, and this one is supported as well. So 4 architectures. Yeah.
So can you suspend at any point in the execution process?
Yeah.
So what happens if you suspend at some point right after you open the file handle, and then you restore it, and that file is no longer there?
Let's talk about it, okay? Okay, thank you.